What does atomic and ionic radius really mean to you? This sounds a bit interesting. They're asking about the meaning of atomic radius and ionic radius. How do you decide the radius of a circle? You start measuring from the center and you go outwards till the boundary. Now, in the same fashion, when we draw an atom, we should be able to say that this is the radius, right? But there's only one problem. And what is that? And that is that an electron doesn't have an exact location. It's a kind of cloud. Now, you can't really determine the radius of a ball of cotton or radius of a cloud because, whatever the reading you maintain or you obtain, it would just depend upon how hard you press or compress. So, ideally, you really cannot talk about the distance from center till the outermost point because there is no fixed outermost point when it comes to electrons or electron cloud. Then how do we measure atomic or ionic radii? Well, the simplest way is this. Within an atom, the only thing you can figure out is the position of nucleus. Experimentally, there is no way, absolutely no way to determine the location of electrons. Theoretically also that seems not to be possible. So what do we do? When we talk about atomic radius, say we want to find out the radius of an atom A. The first thing we check is, does this atom A form bonds like AA? Can it form a diatomic molecule like this? If it can, then what do? I would simply measure the radius or the distance from one nucleus to the other, and this distance D I would divide into two halves like this, and I'll say D by 2 is equal to covalent radius. Please note, I can locate the distance between the nuclei because nuclei are heavy, solid, the location is measurable. I just detect the distance divided by 2 and I obtain a covalent radius. Very obviously, this portion is common. What does that mean? It very clearly means that I am recording something which is a little lesser than the actual possible radius. Why? Because for actual radius, I should have had circles or spheres just touching each other, right? This should have been the case. If they're overlapping, then naturally the distance D is a little reduced. So this covalent radius which I'm obtaining is expected to be somewhat lesser than the actual imaginary radius. But then there is no way I am aware or I can measure that so-called imaginary actual radius. So I just have to be happy with covalent radius. It sounds like we have solved the problem, but there is again a problem. And what is that? The problem is that not every element forms covalent bonds. So, say you have titanium. Now, titanium with titanium or sodium with sodium or magnesium with magnesium, they would form metallic bonds. Oh wow. Then what do? In that case, and since out of 4 blocks in periodic table, 3 blocks refer to metals only, S block, P block and D block, S block, D block and F block. All of them contain metals except hydrogen, of course. So there has to be some other thing also. And what is that? People devise something which is also called as metallic radius. What is metallic radius? The problem is, not all atoms form covalent bonds and not all atoms are metals either. So for non-metals, covalent radius serves pretty well. For metals, you take a metal in solid state, fine, and you determine the shortest distance between 2 nuclei. The shortest distance between 2 nuclei in solid state. And this distance dm by 2, you say, is metallic radius. So if you halve the distance between two nuclei in a covalent bond or a covalently bonded molecule, then you say this is covalent radius. Of course, both these atoms have to be the same. Similarly, if you have the distance between two nuclei in a solid metal, the nearest distance, then you say that is the metallic radius of that element in solid state. In solid state, the moment you're saying, it means that we're imagining that it could be different in different media, but yes, nonetheless. So you have covalent radius and you have metallic radius. Are they the same? No. Metals like sodium have also been found to make covalent bonds. So if you measure covalent radius in sodium and if you measure metallic radius in sodium, you would discover that they are different. But nonetheless, since there is no other way out, absolutely, we just are left with these two methods, metallic radius and covalent radius. And before we sign off, there is one more problem. What? There are atoms which form absolutely no bonds at all, like noble gases. How do we measure their radii? And for them, the idea is just cool them down. Now, I'm not angry. No, I'm not saying you're angry. Just cool the gases down, make them into liquids and finally solids. Take a piece of solid argon, for example. Just like solid metals, if you have a solid piece of argon, a krypton or xenon, try measuring the shortest distance between the two nuclei of noble gases in solid state. Which force actually attracts the molecules of noble gases? Van der Waals forces, right? So in that case, I hope you appreciate that there may not be any overlap at all. It is just that the molecules would be at a certain distance from each other in solid state as per the crystal structure. And this shortest distance between them, you take that shortest distance, whatever it comes out to be, and this distance by 2. This will give you a radius which is called as Van der Waals radius. So we have covalent radius, we have metallic radius, and we also have the so-called Van der Waals radius. Why? Because this is something which is measured between species which are not connected to each other by any solid metallic or any chemical bond, but which are just held together by Van der Waals forces. I hope this is very obvious that this distance is going to be a little more than the actual radius. Why? Because obviously they're not touching because of electrostatic repulsions, they're a little far away. They are a little far away, and hence this radius is going to be, if you're just measuring this, d by 2 would be this distance. This is a little more than radius, right? Whatever. But whatever that comes out to be, since, we can't measure absolutely anything else, we simply say that this is Van der Waals radius. There are 3 ways to measure atomic radius. Either you can measure Van der Waals radius, or you can measure metallic radius, or you can measure covalent radius, and the fun part is that often it is not possible to measure all 3 radii for a single atom, for every atom. So for some atoms, you just have metallic radius, for others you just have covalent radius, for a few you have both metallic and covalent, for some you may have Van der Waals, and so on and so forth. This, my dears, is the story of atomic radius, and this is something which we say atomic radius means to us. Is there a possible relation or the order of covalent, ionic or metallic radius, or not ionic, covalent, metallic and Van der Waals radius? Yes. In a covalent bond, attraction is really strong. They're held, the shared electron cloud is in between 2 atoms, attraction is strong, and that is why covalent radius is always less, because atoms are much closer together. So you find that covalent, the radius covalent radius is always less than metallic radius. Why? See, overall attraction in metals is good, but if you just compare 2 atoms, they just let the electrons get away and they are delocalized in the entire mass. So it's great, but then overall, if you just say the attraction between 2 atoms, that is not as much. So you find they're a little far away and metallic radius is more than covalent, and obviously biggest is Van der Waals radius. So CMV, I hope you can see, it is just alphabetical order, and that also is the order of, incidentally, the order of increasing atomic radii. Covalent radius less than metallic and metallic less than van der Waals. So much so for atomic radius. All this I have spoken about atomic radius. What does ionic radius mean to us? Well, ionic radius would mean either the radius of cation or the radius of anion. Now that is another story altogether. So let's take a look at ionic radius as well. Whenever an atom gains any electron, gain of electron would mean, yes, what would that mean? Gain of electron would mean, well, that it is an anion now, right? If you have more electrons, if you are gaining more electrons, obviously the size will increase. And if you are removing electron, the size will decrease. Makes sense. So you would find that radius of anion is always greater than radius of a given atom, and atom is always bigger than radius of its cation. If I have Na plus or Na minus, Na plus is bound to be smaller than Na atom, and Na minus is bound to be bigger than Na atom, obviously. So if any atom forms a cation, it would become smaller, and if it forms anion, it would definitely become bigger in radius. Yes. What is the radius of ion, and what does this radius indicate? From nucleus till the outermost point, the distance would be termed as the radius. Yes. How do I determine the radius of ions? Well, that's not difficult. Say, for example, you take solid NaCl. If you take solid NaCl and you measure the distance between Na plus and Cl minus, this is radius of cation plus radius of anion. You can experimentally measure this in NaCl, the smallest distance between Na plus and Cl minus, that you could say is the sum of radii of sodium cation and chloride ion. So, radius of sodium and radius of chloride you can experimentally determine. But then you will say, but I don't really have individual values of Na plus and Cl minus. Okay, that's fine. We could actually try more. Why? Just see, instead of this, we could also determine radius of Na plus and Br minus together. Yeah, we can. I mean, these are the values I can experimentally measure. Then I could get potassium chloride also. And I could get potassium bromide also. What are you trying to do? See, sodium, potassium, chloride and bromide are 4 variables, A, B, C, D. And I have 4 equations in 4 variables, and these equations, the right hand side can be determined experimentally. Yes. If I solve them simultaneously, I would get the radius of each of these ions, right? This is how experimentally I determine the radii of various cations and anions using their ionic salts. That's it.